Hello, everybody. I'm Charlie Sharpless. I'm the Assistant Director for Research here at the Andlinger Center for Energy and the Environment. And I'm pleased to welcome you, or for many of you, welcome you back to our summer seminar series, New Light, Rising Stars in Energy and the Environment, which features early career researchers working with faculty at the Andlinger Center. As I previously mentioned, the mission here at the Andlinger Center is to develop practical solutions for a sustainable energy and environmental future through research, education, and knowledge transfer between academia and the broader society. That is a kind of complex effort, and it requires experts from many different disciplines to work together and to work across disciplines, create new areas of knowledge. And it's an effort we call transdisciplinarity, and it's something we try to encourage through our research programs here at the center. Consequently, the presentations that you'll see in the New Light series draw from a variety of disciplines across engineering, material science, social sciences, public policy, energy systems, and more, really depending on where the expertise lies and who's got the motivation to work together across those different boundaries. It's really a fascinating breadth of work, and we're excited to host these outstanding young scholars and to feature their research here for you through this seminar series. Now, the series started 3 years ago, and this is our first year, although it's our second session, but it is our first year with an in-person component. Today, we have two speakers who will speak for about 20 minutes each, with about 10 minutes for Q&A. And because it's a kind of compressed format, I'd ask that if you have any questions, please hold them until the Q&A portion, and then we'll answer your questions there. We do have potentially some people joining us through Zoom, and so if anybody is out there listening on Zoom, I'd ask that you just either use the raise hand feature or the Q&A box to enter questions, and we'll try to address those as well. Our first speaker today is Julie Euvrard. And Julie joined the Andlinger Center as a distinguished postdoctoral fellow in 2021. She earned her bachelor's and master's degrees in engineering sciences from the Grenoble Institute of Technology and completed a doctorate in engineering sciences at the University of Lille. She came to Princeton from Duke University, where she was a postdoctoral researcher with Professor David Mitzi in mechanical engineering and materials science, and where she developed expertise in applying a novel technique called the carrier-resolved photo Hall effect to study charge carrier properties in semiconductors. She is soon going to be off to start her own lab at the Imperial College London in January, where she'll be joining in the Department of Physics as an assistant professor. But while she's been here at Princeton, Julie has been working with Professor Barry Rand to extend the application of the photo Hall effect to characterize organic semiconductors that have applications in photovoltaic materials. Today, Julie will share some insights into organic semiconductors in her talk entitled Organic Solar Technologies: How Does Molecular Arrangement Determine the Fate of Charge Transfer? Julie, it's all yours.
Okay. Thank you, Charlie. Thank you for coming to this seminar where I will talk about organic semiconductors for solar energy. I was planning to do an introduction, but Charlie covered everything. So I will jump directly to the introduction. So as I said, it's going to be about materials for solar energy. No, why solar? Because we can get a lot of energy out of the sun. In just an hour and a half, we get enough energy for the world's energy consumption for a full year. So there's a lot of potential, and that's why we've been developing technologies, including photovoltaics. No, we are still using a lot more fossil fuels than we are using renewable energies such as solar energy. And when we look at this number, the first thing we can think of is, well, solar is still more expensive than petroleum, so it's not that surprising. But actually, that's not true anymore. The cost of solar has dropped dramatically over the last few years and is now even technically cheaper than petroleum. Then why are we still using so much petroleum? Well, it's because we are locked in the way we are consuming energy today. And in order to shift our way of consuming, we need to make some changes, for example, changing infrastructures. And to make this barrier worth crossing, what we need to do is to bring the cost of solar further down. So the two main targets today for photovoltaics are to reduce price and increase efficiency. So far, silicon-based solar cells, which you can buy, have a pretty good efficiency, but the price should be lower. And there is a limit to what you can do. So what we want to do is to explore other options or the candidates that have potential to reduce prices further. And so here's a list of various emerging semiconductors that are looked at in the literature. My research focuses at the moment on perovskites and organic semiconductors. And in particular today, I'll be talking about a recent project I've been doing on organic semiconductors. So what are organics? Those materials are small molecules and polymers that are mostly made of carbon, hydrogen, nitrogen, oxygen, sulfur, which is why we call them organics. And they have a certain number of advantages. They can be processed with a really low temperature. So it can be cheaper to produce than silicon, which needs high temperature processing. You can also target other substrates which are flexible, including plastic or even paper, actually. You can also target large area. You are no longer limited by the size of the silicon wafer. And you can have semi-transparent or even sometimes fully transparent devices. And so those materials have been explored in various technologies. And the most successful one by far is probably LEDs. And you might have OLEDs on your smartphone, or maybe on your TV, especially if you have a curved TV. But those materials are also interesting for other applications, including solar energy. There are still two major challenges for organic solar cell. One is the efficiency. We'd like it to be a bit better, actually a lot better, and stability, which needs to be improved to be able to be competitive on the market. So why is the efficiency of organic solar cells lower than silicon solar cells? It's because those semiconductors behave a bit differently than silicon. And there are various differences. Here I'm explaining one of them, which will be at the center of this talk. And this is related to order. So in most silicon solar cell, it's based on crystalline silicon. And because it's crystalline, it's highly ordered. And so when you have electrons, which are negative charges, and holes, positive charges, which are traveling around into the crystalline, highly ordered medium, it's very efficient. It's like driving on a highway. Organic semiconductors are more disordered. So it's more like taking a mountain road. To travel the same distance, you need a longer time. So transport is efficient in crystalline inorganic semiconductors. It's inefficient in most organic semiconductors. This is one of the differences. There are others, and all those fundamental differences really drive the way we design the devices. You would not design an organic solar cell the same way you would design a silicon solar cell. So you need to understand those properties. And so when you're doing research on those emerging materials, there are different stages. First, you need to create this new material. You need to synthesize it. On the other end of the spectrum, you need to introduce it in a device, for example, a solar cell, and then you can fine tweak thicknesses and this type of thing to optimize efficiency. But in between, there is something that is really important, which is understanding the fundamental properties of those materials, which is really key to then go toward the limit of what you can do with the technology. And so when that's your goal, what you want to do is list the various properties, the various characteristics of your material, which for semiconductors can be divided into three major families. There is a family of things related to type. So is it a P-type semiconductor, an N-type semiconductor? Can you go from P-type to N-type? Things related to transport, which I've already touched on. So how efficiently electrons and holes can travel around. And properties related to how electrons and holes interact with each other, which is especially important in solar cells. Now, accessing those parameters in silicon, no problem. Accessing those parameters in emerging semiconductors, it's another story, and it's actually quite difficult. And that's why I've been collaborating with IBM using one of their tools that they have developed, which is quite powerful and allows us to access all those parameters, even in emerging semiconductors. So today I will answer this particular research question, which is how the way molecules arrange in your semiconductor film will impact transport. And the efficiency of your transport will directly influence the efficiency of your solar cell. And that you can already see it in silicon, where I said that most silicon solar cells are based on crystalline silicon, but you can also have amorphous silicon solar cells, which are cheaper to produce, but they are much less efficient. So order has definitely a role, which we know very well in silicon. What about organics? Organics can also have different levels of order. Most organics will be either amorphous or in what we would call semi-crystalline, where polymers would arrange in a relatively ordered manner. And there are a few organic molecules that can also crystallize. Now, when you look at the literature on transport in those organic semiconductor, what you would find is a study showing that molecule A, which is amorphous, behaves a certain way. And molecule B, which is crystalline, behaves another way. And this can give you an idea that order influences transport and how it influences transport. But molecule A and molecule B are two different molecules. So you cannot really conclude in a very clean manner. So what I wanted to do was to do what's been done decades ago in silicon, where you take just one single molecule that can take various levels of order and look at how this impacts transport without changing the nature of the molecule. And so for that, the ideal candidate is rubrene, which is a very peculiar organic semiconductor. And it's one of those rare semiconductors that can crystallize. And so here we have a very nice polycrystalline film that in this image is a polarized optical microscope image. So each color that you see for each grain is a given crystal orientation. So each grains are highly ordered. Now, what you can also do is induce disorder inside the grain. And you end up with what's called spherulites, where here you no longer have one single color in your grain, but you have a gradient of colors. That means that you have a continuous evolution in the crystal orientation. So you have less order. So that's about order. What we can also change is packing. So here in those films, the molecules arrange in this particular manner in this packing, which is called orthorhombic. Now what you can do is change the packing, and the molecules can form a triclinic crystal phase, and we'll see how that impacts transport. And finally, you can have fully amorphous rubrene. So this offers a perfect playground to look at how order, but also packing, impact transport properties. So let's start with the most ideal case, a polycrystalline film. And now, what do we expect here? Actually, we know that in a single crystal, so in one of those grains, transport is band-like. Band-like transport is what's happening in silicon, where electrons and holes can travel very efficiently. They are delocalized, and it's like rolling down a slope. It's very easy. Now, this particular transport properties has certain characteristics that we can measure experimentally. So for example, we know that for this transport, the conductivity should decrease with increasing temperature. What does it mean? It means that when you increase temperature, transport becomes less efficient because the system is vibrating more, and so you're messing up with the order. That's one characteristic. Another one is related to Hall effect. So what is Hall effect? Is when you apply a current and a magnetic field and you end up with the Lorentz force. So if you apply a current here in this direction on the semiconductor and you have a magnetic field in the perpendicular direction, then what's happening when you have the Lorentz force is that this force is deflecting your charges away from their direction, and you end up with a bias in the transverse direction. That's a Hall effect that you can measure. Now, an interesting thing is that only those band-like carriers, the carriers that are behaving that way, do feel the Lorentz force. So if you can measure a Hall effect that has a reasonable value, then you most likely have band-like transport in your polycrystalline film as well. So here are the results, starting with Hall effect. And I won't enter into too much details. I don't have much time, but what I will highlight is that those measurements have been done at IBM with this highly sensitive setup. that relies on an oscillating magnetic field that has a single harmonicity, which means that it oscillates at one frequency. So here you have the magnetic field in the frequency domain, and it oscillates at this given frequency. And this allows you to extract the whole resistance on the bottom graph at the same frequency, even though you have a lot of noise. So it really allows you to get the signal out of the noise here. And when you calculate values out of the signal, you can calculate the density of carriers, how many carriers you have, and the mobility, so how fast they can travel. And what we see is that those values are fully consistent with what we expect. So this tells us that transport is most likely band-like in this polycrystalline film. What about conductivity? So here you have conductivity. Just pay attention to the x-axis. It's as a function of inverse temperature. So the highest temperature is actually on the left here. And what we obtain is the opposite of what we would expect for band-like, because the conductivity is increasing with temperature here. But it's not inconsistent with band-like, and I'll explain why. What we think is happening is what is happening in polycrystalline silicon, actually. You have band-like transport inside the grain, but then when the charges have to travel, they have to cross certain grain boundaries. And those grain boundaries are not energetically favorable. So you have to provide energy to the charges to be able to jump over this barrier. So in the end, what we see is that transport in polycrystalline rubrene behaves in a very similar way as transport in polycrystalline silicon. What about the other extreme case, amorphous? In that case, band-like doesn't hold anymore. What you need to consider is hopping transport. So what is hopping transport? It's when you have a charge that is sitting on a molecule, and to travel around, it has to hop from one molecule to the next. And for that to happen, you need to provide energy. And so typically what you will have in that case is a conductivity that increases with increasing temperature. So by providing thermal energy, you make transport more efficient. But an interesting thing is that those hopping carriers do not feel the Lorentz force, which means that if you had pure hopping, no band-like whatsoever, you shouldn't have any Hall signal at all. So let's see if that's what we have. First, conductivity. You have the data for amorphous in red here. The first thing you can notice is that at room temperature, the conductivity is almost 5 orders of magnitude lower than polycrystalline. This shows you how order can be important because it's the same molecule and the order has a dramatic impact, which is actually quite reminiscent of what we see in silicon, where we also have many orders of magnitude difference between the conductivity of amorphous silicon and crystalline silicon. The behavior with temperature is what we expect for hopping transport. Now, what about Hall effect? Well, actually, we do have a peak here. So we do have a Hall signal. It's not pure hopping, but when we extract the data out of it, we obtain a density that is 5 orders of magnitude lower than what we should expect. And this is because this technique is only sensitive to the band-like carriers, but do not see the hopping carriers. And the vast majority of carriers here are hopping. So this film is not purely hopping, but mostly hopping, which is also what we observe in amorphous rubrene, especially when we go down in temperature. Now, what's happening in between? I said you can induce disorder inside the grain. And interestingly, when we look at the experimental results, we obtain something in between. We have a conductivity that is in between those two extreme cases, an evolution with temperature that is also in between, and the density we get from Hall effect is also between what we expect and the most extreme case of amorphous. So what we conclude from that is that when you go from highly disordered to highly ordered, you're going from one transport mechanism, which is mostly hopping, which is inefficient, to another extreme where the transport mechanism is very different, band-like, and much more efficient, but you're going in a very continuous way. You're not going from to the other suddenly, you're going in a continuous manner. Okay, no, there's something we cannot do with silicon, which is change the way the atoms pack. At ambient pressure and temperature, crystalline silicon will only form in a certain crystal phase. Now, in rubrene, you can actually have different crystal phases. So you can also look at how packing can impact transport. So as I said, here you have a certain packing, which is different from the packing here. And when we look at the transport properties, we observe that actually, surprisingly, the data are very similar to Amorphous. Here you have in orange the triclinic. And the same thing happens in Hall effect. We obtained very similar data between triclinic and Amorphous rubrene. So that means that even though this is, so I should mention that the triclinic phase is not a super ordered phase, but it's still more ordered than the Amorphous film. And still, there is no improvement in transport properties. So overall, what do we conclude? We conclude that sure, order is important, and we see that by increasing order, for example, by increasing order inside a grain, we can dramatically improve the transport properties. But it's not sufficient because we have also increased order in this triclinic film, but we have not improved transport properties at all. That's because the packing is totally inappropriate. So if you want to really design the ideal molecule, you need to design a molecule that will interact with each other and pack in the solid phase in a way that is appropriate for electrons and holes to travel around. And with that, I'd like to thank the Untitled Center for the fellowship, which allows me to do the research that I really enjoy. My collaborator, Oki Genawan at IBM, my mentors, Antoine Kahn and Barry Rand, all the members of the Rand Lab, the Kahn Lab, and of course, thank you for your attention.
Does anybody have questions for Julie?
For the transport of charges across grain boundaries in the polycrystalline case, how does that barrier compare to the barrier of charge transport between the crystallites and the spherulites that are like just slightly misoriented from one another?
No, so I have data that made me believe that the energy barrier would be higher in the case of spherulites. Oh, you mean inside the grain?
Yeah.
Oh,
within
inside.
a single grain.
Oh, okay.
Because right, the little crystallites
Yeah.
are just slightly offset from one
Yeah,
another.
that I don't know. That I don't know.
But is it expected to be substantially lower than a real grain boundary?
I would guess so. But yeah, no, I don't have the data for that. I wouldn't know.
Okay.
Yeah, what I was about to say was
Yeah.
the grain boundaries between big grains of spherulites, which our data suggest that it would be higher, but it could also be a different transport mechanism. So it's really hard to conclude for sure.
Thank you for the talk. What considerations do you think would have to be set in place to, I guess, realize these different crystalline morphologies of rubrene for an actual solar cell setup? Like, do the semi-crystalline and crystalline and amorphous phases all exist at room temperature at the conditions necessary for a solar panel?
Yeah, they all exist. You can all form them at room temperature. And actually, there's someone, Holly, in the Rand Lab, who is working on solar cells with amorphous and crystalline rubrene. So maybe in a few months, she'll be able to say something about it. I don't know if Holly hears me. But yeah, I mean, if the question is how that impacts, is the question how does it impact solar cells?
Well,
or
if we find that this varying degree of crystallinity is ideal for charge transfer.
Charge transfer.
Or conductivity, right?
Conductivity, yeah.
Yeah. I was just asking if it's if it's possible to realize that technology at larger scales, and it sounds like it is.
Oh, larger scales. Yeah, it's actually forming crystalline film of rubrene is quite difficult, but it's possible. So I'd say it wouldn't be easy at large scale, but I guess with some optimization, it could be possible. Yeah, but I mean, rubrene is probably not the best candidate actually for solar cells. Here, I used it because it was really the perfect candidate for this particular study to end up with more general rule, but there are other organic semiconductors that are much more promising for solar energy.
And you'd expect the results here to transfer to those other organic.
The result that I expect to transfer is that the packing is important, and actually there've been organic semiconductors that are amorphous that transport quite well. So even if you have an amorphous film, but the side change of the molecule can interact with each other in an appropriate way, then you can still have appropriate transport. So I think what is really key is not necessarily order, but really the way the molecules interact with each other.
Here and there.
So I wanted to ask kind of a couple of questions about the boundary between hopping light transport and band light transport. So the molecule kind of has its little potential surface, and the closer you pack them, the lower that barrier gets between. So is how we think about the difference between, or the transition between hopping light and band light, sort of just the height of that barrier? And then I wanted to get your thoughts on basically what the fundamental difference is between hopping and band that prevents the Hall effect from being active in a hopper.
Okay, so the fundamental difference between band light and hopping is that hopping is carriers in hopping are really sitting in a molecule. So as you said, it's like being in a how do you say that? In a hole, and there are energy barriers on both sides. Now, in band light, you're really forming bands, which is what we see in crystalline materials. So in that case, we say that the charge is delocalized in the sense that it's no longer sitting on one molecule, but it's existing on several molecules at the same time. So that's a fundamental difference. So to me, it's still unclear if there is like what is the transition, because there is actually literature on the fact that you can be delocalized over a certain number of molecules, and depending on how many molecules you're delocalized on, your transport is more or less efficient. So it seems to be continuous in a way to go from purely hopping, where you really sit on the molecule, and fully delocalized. But to me, it's not fully clear. Now, what was the second question? I forgot.
So I kind of maybe partially answered it there, but looking at Hall effect and
Hall
looking at
effect,
why Lorentz force doesn't apply to hoppers.
Yeah.
If you have something that's hopping pretty fast, wouldn't you still see?
Yeah. That's related. So it's at the limit of what I can cover. What I know is that hopping carriers that are localized are not coherent, and carriers that are delocalized are coherent, and only carriers that are coherent can feel the Lorentz force. So that's the limit. And what I think is happening in Amorphous is that they are delocalized over maybe just 2 molecules or maybe 3, and that's enough to see a little bit of Hall effect, but it's not enough to see the proper Hall effect.
Do you know if the morphology of these rubrene systems changes substantially after passing current for a sustained period of time?
I don't think so, but I've never really measured it. What are you thinking of something specifically, or?
As in if the crystalline becomes more amorphous over time?
Yeah, no, I don't think so, because I usually, after I measure the conductivity, I always go check the polarized optical microscope image, and I never saw anything that really struck me. So I don't think so.
I have one quick question, which is you showed the, I guess it was when you switched to amorphous, the current density, I assume current drop by 5 orders of magnitude, and you saw almost exactly the same drop in the carrier density measured by the whole thing. Those are directly related, right? Is that too simplistic?
I think it's related because it would be too much of a coincidence, but I don't know why.
Well,
I
it
don't
just
know.
seems like the density of the carriers
Yeah.
should be directly
But-
proportional to that.
But the density shouldn't change. The real density shouldn't change. What changes is the mobility when you go from crystalline to amorphous. So it's too much of a coincidence to be the exact same orders of magnitude, but I don't know how to explain why.
All right, if we don't have any other questions. Thank you, Julie.
Question. How'd that happen?
There's a question. What? Question in the chat.
There were,
Next.
I don't think there was a question in the other
Was there,
room.
was there a question in the other room?
There's a question in the other room.
Oh, no.
Here, stay up, stay up.
Oh, what? Oh, there's a question?
I don't know how to take a question from the other room. Please speak up if you have a question.
Thank you, Julie, for your presentation. I was wondering about the, based on your experience, what are the strategies to increase the efficiencies? Because as far as I'm aware, in the silicon-based photovoltaic panels, you want to the arrangement of materials, not only to silicon only, but also others, but including others, to modify the band gap. And what are the strategies do you see to increase the efficiency in these organic materials? And the second question is that how do you see, or what is the potential of recyclability in terms of circular economy? Picture, is it similar to current polycrystalline silicon? Thank you.
Okay, I'll try to answer the. So for the second question, I honestly don't know. I really don't know what the recycled yeah, no, I won't say something accurate. So I prefer not to answer, to be honest. First question, I didn't fully hear it. I think how to improve, what the strategy to improve efficiency, I think it was. Was that the question?
Yeah.
Yeah, just say, please speak, if you're speaking from the other room, just speak up. You were dropping in and out a little bit, so it was difficult to hear the question. You could just come over here.
But I think I can answer broadly. So I think the strategy, so today I covered only one major difference. For this particular major difference, I think it's about thinking about molecules that pack in the appropriate way. But there are many other differences that we need to cover, many problems that we don't see in silicon and that we see in organics. I should also say that there are good things in organics that are better than in silicon. But yeah, so there are many other things that we need to consider that I didn't cover today. But for my part, it would really be the way molecules interact with each other.
Thank you.
Thank you, Jim. All right, our next speaker is Allyson McGaughey. Allyson joined the Andlinger Center also as a distinguished postdoctoral fellow in 2021. She earned her bachelor's in chemical engineering from the University of Washington and her master's and her doctorate in environmental engineering from University of Southern California, where she made key advances in understanding how the chemical and physical properties of porous membranes control their performance in desalination via membrane distillation. Here at Princeton, Allyson is working with professors Rod Priestley and Jason Wren to develop new polymers and fabrication processes that will enable production of water treatment membranes that resist fouling and enable better process efficiency and longer material lifetimes. Today, she'll present some findings from this work in her talk entitled Scalable Polymer Brushes, New Materials for Water and Resource Recovery.
Share my screen here. All right, hopefully that looks good. Let's see. Okay, thanks for the kind introduction. I'm excited to be here and thanks everyone for coming. I've enjoyed all the talks last week and today. So yeah, today I'm going to be talking about the materials I've been working with over the past year for water and resource recovery applications. So to start out with some motivation. So membrane separation processes are critical both for securing our future water supply and to enable a circular water economy. So this animation shows water stress projected from 2020 through 2040, with the darkest red areas indicating extremely high water stress. So if you keep your eyes on the darkest red areas as I transition to this map. So here we have installed desalination capacity around the globe. And you can see that the areas that are experiencing highest water stress are also those that are using the most of these alternative sources. So water stress is driving suppliers around the globe to rely more on these new sources of water. About 70% of these facilities rely on reverse osmosis, which is a membrane process for the key separation step. And also the majority of those rely on membrane filtration for pretreatment. So this transition has been going on for several years. And the water sector is also undergoing this paradigm shift right now towards a circular water economy. So no longer based on a treatment and discharge framework, but based on a framework that relies on reuse and resource recovery. And membranes are key parts of enabling that reuse and that resource recovery from waste streams. So as we seek to use membranes to recover water and other valuable resources from increasingly complex waste streams, fouling is an increasingly critical concern. So fouling is just the accumulation of foulants, which may be biological material, organics, oils, and inorganics, also known as scaling, on membrane surfaces. And this blocks the pores of our membranes, which increases energy consumption and reduces the lifetime of our membranes. So these are just some images I pulled online, so of some nice clean membranes, and then after use in a bioreactor, so these are microfiltration membranes, and this is an RO membrane, and then after use in desalination. So as interest in fouling increases, this is reflected by this exponential increase in the number of publications per year that focus on membrane fouling, which has been followed by an increase in publications focused on anti-fouling membranes. And so anti-fouling materials have several benefits. They can improve the energy efficiency of these energy-intensive processes. They can reduce our operating costs. They can extend the lifetime of our membrane materials. And maybe most importantly, they can enable resource recovery from more challenging sources. Okay, so the anti-fouling material that I've been working on over the past year that I'll talk about today are polymer brush layers. So polymer brushes are thin films of polymer chains that are grafted or covalently bound to a surface at one end. So as illustrated here, as we increase the grafting density of our chains, they're sterically hindered and they're forced to extend outward from the surface. And that results in this kind of brush bristle-like layer that we see here, where TB here indicates the thickness of our brush. And we can control the thickness and the structure and the surface chemistry. So one surface chemistry in particular, Zwitter ionic polymer brushes, have shown great potential for anti-fouling layers. So Zwitter ions are characterized by an equal number of cationic and anionic groups, so they have a neutral overall charge. And when we put them in water, they form these substantial, strongly bound, and also unstructured hydration layers. And this gives us very strong hindrance to the attachment of various types of fouling. And the polymer brushes themselves also provide steric hindrance because they resist compression. So this is all great. They work really well. What's the problem? So traditional methods for brush fabrication have very limited potential for commercial scale up. So traditionally, polymer brushes are fabricated using surface-initiated atom transfer radical polymerization, or SIATRP. So in SIATRP, our reaction occurs in bulk solvent. And here we have the equilibrium reaction. So our substrates are functionalized with initiator sites. These are alkyl halide groups, and these react with an activator. This is typically a copper catalyst in the lower oxidation state to form radical sites, which react with monomers to form our growing polymer chains, and also producing a deactivator species, which is just our activator in the higher oxidation state. So for this to proceed, the environment has to be completely oxygen-free, and this is to prevent scavenging of our radicals as well as oxidation of our activator. We also have to add our catalyst in the reduced state, so not exposing it to oxygen prior to addition. And these factors severely limit potential for commercial scale up because it's hard to achieve this other than in a very controlled lab environment. So there's been significant efforts to address this, including adding reducing agents to the reaction solution. So in RGET ATRP, a chemical reducing agent is added, typically ascorbic acid. In electrochemical ATRP, an electrical current is applied. And this allows us to add the activator in the oxidized state, and it relaxes our need to deoxygenate, but they do still occur in bulk solvent. So the variation I'm going to focus on today is called zero valent metal mediated ATRP. So in this scenario, we use a zero valent metal, typically copper, as the reducing agent, as well as the oxygen consumer, and it can act as an in situ source of our activator and our deactivator species, as I will show here. Okay, so in copper-mediated ATRP, so we take a copper plate, we bring that into contact with our reaction solution, and we bring that into contact with our initiator functionalized substrate. And if we leave this at ambient conditions for some time, this will result in polymer brush grafting. So if we imagine zooming in on our reaction here, so polymerization occurs in this thin film of solution between the copper plate and the substrate. So when the copper plate contacts the reaction solution, it consumes dissolved oxygen present, and copper also dissolves, and that forms our activator and our deactivator species according to this discomproportionation equilibrium. So as these species diffuse to our substrate surface and they reach initiator sites, they will react according to that conventional SI-ATRP equilibrium, and we get our polymer brushes. This parameter D, which is the distance between the copper plate and the substrate, is also enables additional control over our brush growth. So this was introduced in 2015 by Zhang et al. And importantly, we can achieve polymer brush grafting under ambient conditions, so no deoxygenation required. We also can achieve, or exceptional brush growth rates and grafting densities have been reported in the literature. And chemical consumption is very low because only a very small volume of reaction solution is required just to fill this thin gap between the substrate and plate. So it has yet to be reported to our knowledge for membrane modification. So I'm going to show you that today. So that brings me to our objectives. So our first objective is to demonstrate copper-mediated ATRP for brush grafting from membrane substrates, and specifically looking at these porous substrates, as I've illustrated here. And our second objective was to evaluate and try to understand the effect of polymerization methods and parameters on brush thickness, as well as fouling resistance. So specifically, we expect increasing that distance D between the copper plate and the substrate to result in higher brush thicknesses. And based on studies of conventional brush membranes, we expect that to result in better fouling resistance. So I'll just briefly introduce our methods. So I'm going to show you results for polymerization of polysulfobaniene methacrylate brushes. This is a Zwitter ionic material that's been shown to have very high fouling resistance. For substrates, so I'll show you results for modification of this microfiltration PVDF membrane, as well as for brushes grown from initiator functionalized silicon wafers, which allows us to characterize brush properties using ellipsometry. And in terms of methods, so we looked at 3 different methods that have been used in the literature. So the first I'm going to call the load method, just for short. So in this scenario, we place a load or a weight on top of our substrate to bring it into contact with reaction solution. And this gives us a very small distance D on the order of 5 to 10 microns. The second is what I'm going to call the spacer method. So in this case, we're just using some spacer material to maintain a wider distance D between our substrate and copper plate. This is typically 1 to 500 microns. And then the third method is what I'm going to just call the filter paper method for short. So this was recently introduced by Li et al. So in this case, we're wetting filter paper with our reaction solution and placing that between the substrate and copper plate. And that will give us a distance equal to the thickness of the filter paper, typically 1 to 200 microns. So the load and spacer method, these kind of thin film methods, have been reported to result in high brush growth rates as well as moderate to very high densities. The filter paper method was reported by Li et al. To give higher brush growth rates, although the brush densities reported were slightly lower. So we were interested in comparing these to look at both brush growth and fouling resistance. Okay, so towards our first objective, so looking at modification of membranes using this method. So here we have our microfiltration PVDF membrane. This membrane is relatively hydrophobic. It has a contact angle of approximately 130 degrees before and after plasma treatment. So after modification with our brush layer, and I'm going to start here with the load method at our smallest distance D, and this is after 1 hour of polymerization time. So we see that water readily spreads across the surface, indicating the presence of these hydrophilic brushes. For the spacer method, so increasing D here, we now see that water is actually absorbing into the membrane. So you can see these kind of transparent areas here where it's fully wetted. And for the filter paper method, so here increasing D again, but also using filter paper, we see spreading across the surface, although it's somewhat more heterogeneous. So to further confirm the presence of our brushes, we also looked at XPS results. So this gives us the surface elemental composition of our samples. So this shows the unmodified membrane in the darker gray, and we also have the unmodified membrane after plasma treatment in the lighter gray. So we see peaks here for fluorine and carbon, that's associated with PVDF, and we also see a small oxygen peak after plasma treatment. After brush growth, so starting again with the load method, and here we have 10, 30, and 60 minutes polymerization time. So in all cases, we see a higher oxygen to carbon ratio, and we also see peaks associated with nitrogen and sulfur, which tells us that our brush layer is present. And we see very similar results for both the spacer method and the filter paper method. So confirming that in all cases, with all methods, we can achieve brush growth. Okay, so that's our first objective. So now we wanted to look at the effect of these polymerization methods on brush growth and fouling resistance, but I'll start here with brush growth. Okay, so now I'm going to show you results for brush thickness measured from initiator functionalized silicon wafers, which, as I mentioned, allows us to use ellipsometry for higher accuracy. And here we have brush thickness versus polymerization time, starting as always with the load method. So we see an initial increase in brush thickness, and it's relatively stable after 10 minutes at about 16 nanometers. For the spacer method, so increasing D now to 150 microns, we see that initially brush thickness is higher. It also increases with polymerization time. And I'm going to show you increasing D just at 60 minutes polymerization time. So if we go up to 300 microns, we increase brush thickness further, and again at 500 microns. So now bringing in the filter paper method. So with this first filter paper, it has a thickness of approximately 120. We see a pretty high brush thickness. And with this second filter paper, about 220 microns thick, we actually see a pretty similar brush thickness. So we're varying D here. So we can also look at brush thickness versus D, which is what I'll show you over here. So here, starting with the load and spacer methods, all of these thin film methods, we see a pretty strong linear relationship between brush thickness and that distance D. But when we bring in the filter paper methods, we see a higher brush thickness than expected. So this indicates that filter paper, in agreement with what Lee et al. Showed for a different monomer, we can accelerate brush growth. And that's likely due to reduced concentrations of our deactivator species at the membrane surface. All right, so moving forward, I'm just going to show you results for these three methods. So load method, spacer at 150 microns, and this filter paper at 220 microns as we look at fouling resistance. All right, so now on to the second half of our second objective. Okay, so to characterize fouling resistance, we use colloid probe force microscopy. So this is an AFM-based technique in which we use a colloid probe to characterize adhesion forces. So we use two probes. The first one is this carboxylic acid functionalized polystyrene particle. This is representative of an organic foulant. And then the second one, we used a soft hydrophobic polyethylene particle, which is representative of an oil foulant, so a soft hydrophobic foulant. And we perform all measurements in a low salinity electrolyte solution. So we bring our probe into contact with our substrate, and then we retract, and that results in a force distance curve, something like the example shown here. And then based on the maximum depth of our retraction curve, we can determine the adhesion force between our colloid probe and the substrate surface. So the higher the adhesion force is, the more likely the foulant is to attach. So that's bad. We want low adhesion. Because these are stochastic in nature, we perform this many times for each substrate, and that gives us an adhesion force map like the one shown here. And each of these figures represents 400 force curves. Okay, so starting with our organic foulant, our model organic, and here we have our unmodified membrane, and these are just the same results from the previous slide. So all I want you to really focus on here is the color. So the higher the adhesion force is, the worse. So basically we don't want to see any red. We want to decrease the adhesion force to improve fouling resistance. We can also look at this quantitatively by looking at a histogram of our adhesion forces. And here we have the average adhesion force and also the variance, both of which are relatively high for this unmodified membrane. So after modification with our brush layer, and starting again with the load method. So here we have a brush thickness. It's relatively thin, about 16 nanometers, but we've improved fouling resistance dramatically. And we can see this quantitatively. We've reduced the adhesion force by an order of magnitude, and variance is also close to 0. So that's looking good. For the spacer method, if we increase D and we also increase brush thickness here, we see a further improvement in fouling resistance. So the average adhesion force has gone down a little bit further, and variance is also almost equal to 0. Okay, so what about when we go to the filter paper method? So we've increased brush thickness here by quite a bit, but we actually haven't improved fouling resistance. In fact, the average adhesion force here is an order of magnitude higher than for the spacer and the load methods, and variance is also much higher. So this is especially interesting because previous studies of brush modified membranes have focused almost exclusively on thickness to improve fouling resistance. But we're seeing increasing thickness. Actually, fouling resistance is going the opposite direction. So that's organics. We also looked at, as I mentioned, a model oil foulant. So here we have this adhesion force map for our model oil foulant for the unmodified membrane. We can see that this membrane has very low fouling resistance to oil, which we expect because it's a hydrophobic membrane. So looking at this in terms of the histogram, we can see that the average adhesion force and variance are very high for this membrane. So for our brush modified membranes, starting again with the load method, so we can see that we've improved fouling resistance dramatically. At this scale, we don't see any colored pixels. And looking at the histogram here, we can see that the average adhesion force is decreased by an order of magnitude, and variance again close to 0. When we go to the spacer method, so increasing brush thickness here, we don't see much of a difference visually. But looking at the histogram, we can see that we've slightly improved the average adhesion force with similar variance. So these are pretty similar, but performance is good. But then when we go to the filter paper method, even at higher brush thickness, yet again, we're seeing lower fouling resistance. So the average adhesion force here is an order of magnitude higher than for both the spacer and load methods with a much higher variance. So yet again, increasing brush thickness, increasing fouling resistance is actually going the opposite way. Okay, so that brings me to our takeaways. So first, I hope I've convinced you that copper-mediated ATRP is a viable method for scalable polymer brush growth on membrane substrates with commercial potential. And second, we looked at how increasing D and different methods, particularly the filter paper method, can accelerate brush growth and increase brush thickness. However, brush thickness alone does not determine fouling resistance. In fact, our results imply that the homogeneity and the brush density are likely even more important than the brush thickness when we're considering how to design robust anti-fouling surfaces. So with that, I'll conclude by thanking my funding. So I'm also supported by the Distinguished Postdoctoral Fellows Program here at the Andlinger Center. And of course, my research groups, especially my advisors, Professor Rod Priestley, Professor Jason Wren, and my co-authors on this work, Sneha and Kofi, who are here, and all my lab mates. So thank you.
We'll open the floor to questions.
Yes.
Thank you so much for the talk. It was great. I have two, like one question and one kind of like comment, or hopefully something to spark discussion. Do you have any mechanistic insights on why increasing the thickness actually decreases the anti-fouling performance?
Like for the membranes?
Yeah.
Yeah, so I think it's likely I'm thinking it's either lower density or that there's more defects present for this filter paper method. So when we insert, material with its own surface roughness and porosity here, in some areas we have a distance equal to the thickness of the pore, but in other areas we may have contact between the material and the membrane. So in those areas, we're likely getting much thinner brushes, or as I, kind of illustrated here, maybe no brush growth. So it's probably like a lower density, either at a macro scale or a micro scale, that's resulting in lower fouling resistance. And in terms of the zwitterionic layer, I guess potentially like a more dense layer, even if it's thinner, might give us a stronger hydration layer, which gives us better resistance to attachment, and then better like steric hindrance with the brushes. So that's my guess, but we are looking into characterizing density right now. It's a little bit tricky.
Yeah, I can even.
So yeah.
Also, yeah, the second thing was, is there any, because it was a relatively recent technique, the one about like the sticking the two materials together to get that,
Yeah.
right? So has anyone looked at prospects of making it large scale? Because there's you remember in what I presented last week, it was tangential, but I talked a bit about the Landau-Levitch problem, which is essentially you draw a plate from a bath of a very viscous liquid and you want to see what the film thickness is. There's a lot of studies of that on, instead of just a plate, like a roller or something like that, because it's super frequent in industrial processing, which you want to coat something, and studying the fluid mechanics of that give you a very good idea of what the film thickness is. So it could be a prospect for like large scale implementation of this, because it is just like if you want to make a continuous processing, which you have like this, something like that.
Yeah, a roll to
There's just
roll.
yeah.
Yeah, that's a really interesting point. I think that would be very interesting to look at. And I don't think anyone's actually talked about scale up of this on like a detailed level. People just say, it seems very scalable. But yeah, I think that's a really good point. That would be really interesting. Thank you.
Thank you for the talk.
Thank you.
As I understand, the thickness growth of your brush layer is determined by more and more molecules absorbing and pushing each other and getting more straight, right?
Yeah, I guess there's that, and also just as we add monomers, they grow over time.
So do they grow on top of each other also? Like, do they add up?
Yeah, so I guess as we from the radical site, so it'll react with monomers and it'll add piece by piece. So the longer we let it react, the longer the brush grows. But then there's also that effect, as you mentioned, of if they're far apart, they'll be more collapsed. And if they're closer together, they'll extend further outward. So yeah, I guess there's two.
Well, that answers my question. Thank you.
Okay, thank you. Yes.
If you were to use these anti-fouling films in a real application, would you expect any like changes in the selectivity or permeation of the films?
Like through the membrane.
Yeah, through the
Yeah,
membrane.
definitely. So that's kind of another optimization point, is like as we're adding material on top of our membrane, potentially blocking the pores. So yeah, we do expect that to affect permeability. And there's probably some optimal point, which people have looked at with respect to thickness, where if you grow too long, you're decreasing the permeability of your membrane. And so that reduces performance separate from fouling. And I think there could be something interesting here to look at how density affects permeability. Maybe a denser layer, but thinner, will allow us to achieve higher permeability, but also the same or better fouling resistance. But yeah, I think that's a very interesting point. Hopefully that answered. Yes.
Hi, Allyson. Have you ever considered the growth of polymer brushes inside the pores?
Yeah.
So, because once you apply like the thin film there, a lot of them gonna go inside the pores, and then most likely some of the polymer brushes gonna grow inside that. And I think another interesting point is like how deep it can penetrate into the pores.
Yeah, that's a really good point. And so that is something we considered, especially with, I don't know, I won't pull up the picture, but with the spacer method, we saw a wetting of the pores. And so one possibility is that we were getting interpore brush growth there. The one interesting thing is so the way we functionalize our membrane substrates with initiator sites is plasma treatment, and we don't expect any initiator sites within the pores. Like we don't expect initiator sites on the pore walls, just because the mean free path is too big to get in there during plasma treatment. However, we maybe are getting brush growth just into the pore space, because the thickness of the brushes is, orders of magnitude lower than the pore width. So I'm not sure how to actually characterize that yet, but it is interesting. And there is a paper looking at a different method for ATRP that discussed, actually driving interpore brush growth as a way to get better fouling resistance, because you don't want irreversible fouling inside your pores. But yeah, I think that's kind of an
quick
answer.
follow-up.
Yeah.
Does that mean that the polymerization solution doesn't wet the fibers?
It does wet the membranes.
It
Yeah.
does wet.
Yes, it does. And we do actually see brush growth on both sides. So I kind of trimmed this talk down. I'm only talking about the side we care about, which is the feed side. But it does, water or reaction solution will diffuse through the membrane and reach the other side. So, but we don't expect initiator sites on the pore walls.
Okay.
So we only expect brush growth from the surface. But the way I drew it is outward. It's possible that it's growing inward too, in my opinion. Yeah.
we have other questions in this room? Do we have any questions from the other room?
This time, thank you.
Very simple question for me to
Yeah.
understand. How are you measuring the brush length? And how would you characterize the density?
Yeah, so we're measuring brush length using ellipsometry. So it's a light-based technique based on the reflection and the transmission of light through the transparent film. And that we can only use the silicon wafers because they give us like a different, a non-polymeric substrate to measure off of. So measuring off of membranes is a lot trickier. There's been I think one interesting study where they used kind of like a silver binding technique where they bound silver ions to functional groups on the brushes, and then they measured the concentration and tried to relate that to brush length. That depends on the brush you're using, so it is tricky, but we're using ellipsometry right now, and we've seen good agreement between growth off of the silicon wafers and off of spin-coated PVDF films. And then brush density is tricky, so you can cleave your brushes off and then concentrate them and put them through a GPC and measure the molecular weight. Sneha can tell you a lot more about that than me, but it's challenging to do. So we're kind of interested in looking at this AFM-based technique, where we're going to try to measure the swollen thickness, and then you can relate the thickness of the brush in a good solvent where it wants to extend to the brush thickness when it's dry to the density, because they'll be able to swell, I guess, more if it's less dense. So that's something that, yeah, we're working on now, but it's kind of a tricky problem.
And then my other question is, you showed the, for the AFM measurements of fouling resistance, you have the oil-like and the,
Yeah,
I guess the sort of more hydrophilic like surface.
yeah,
What about ions?
yeah.
These look like ion exchange membrane components, right? So
Yeah,
they're gonna bind.
that's interesting. I'm not sure how you would do that with AFM. I think there has been some interesting stuff with functionalizing the probe with like a salt crystal to try to measure scaling resistance, but yeah, as far as ion attraction to it, I'm not sure. That's something I would have to think about more. But yeah, that's an interesting point.
It was just the scaling resistance. Yeah.
Yeah. Thank you.
Well, thank you, Allyson. I'd like to thank everyone for coming. I'd also like to thank the staff at the Andlinger Center, particularly Rob Ike, who's worked really hard to make sure this is a successful series and everyone's well fed and we're all comfortable and all the technology is working. This concludes the series for this summer. So I hope to see many of you at future Andlinger Center events, and hope you guys have a great rest of your summer. Thanks again.
Yes, at the end I saw